In this video, we'll talk about enthalpy of reaction. Both internal energy and enthalpy are state functions. Remember, H is equal to E plus PV. H, E, P, and V are all state functions. A state function only depends on the current state of the system. It does not depend on how the system reaches that state. Therefore, the change of the enthalpy of a system is equal to the enthalpy of its final state minus the enthalpy of its initial state. For a chemical reaction, we know the enthalpy change is equal to the enthalpy of the products minus the enthalpy of the reactants. Why? Because its final state is the products. Its initial state is the reactants. Let's work on one example problem here. For a chemical reaction, let's say it's 2A react to produce 2B plus C. There's a good example here. 2 water molecules may decompose into 2 hydrogen molecules and 1 oxygen molecule, or 2 moles of water can decompose into 2 moles of hydrogen and 1 mole of oxygen. So in general, let's say we're looking at a chemical reaction in which 2 moles of A react to produce 2B and 1C. And then how do we compute the enthalpy of reaction? Very simple. That's just the enthalpy of the final state minus the enthalpy of the initial state. The enthalpy of the final state is the enthalpy of 2B and a C. The enthalpy of the initial state is simply the enthalpy of 2A. Therefore, the enthalpy of reaction is simply 2 times the enthalpy of 1B plus 1 times the enthalpy of C minus 2 times the enthalpy of A. Let's assume for this chemical reaction, we know the value of the enthalpy of reaction. Let's say it's positive 600 kilojoule per mole. It's positive, and then we know it's endothermic. Heat flows into the reaction, and then it also means we need 600 kilojoule of heat flows into such a reaction system to convert 2 moles of A to 2 moles of B plus 1 mole of C under the isobaric condition. So you may ask, why did I emphasize this isobaric condition? Well, if I change this word to isochoric, and then this equation this statement does not hold true. If it's isochoric, then the internal energy change of the reaction is equal to the heat flow. So let's get back to this equation, and for 2A to react and produce 2B plus C, we have this enthalpy of reaction is equal to 2 times the enthalpy of B plus 1 times enthalpy of C minus 2 times enthalpy of A is equal to 600 kilojoule per mole. Okay, I made up this value just for convenience. And then let's look at a different equation. Now this time, I'm going to start with 1 mole of A and produce 1 mole of B and 1/2 of C. What's the enthalpy of reaction for this one? Well, very simple. Again, you write out the enthalpy of reaction, which is the enthalpy of the products minus the enthalpy of the reactant. Therefore, it's the enthalpy of just 1B and the enthalpy of 1/2 of C minus the enthalpy of 1A. And if you compare this expression with the above expression, you will see this expression is simply 1/2 of the previous expression. Therefore, the result is just 1/2 of 600. What if I reverse the direction of the reaction? Now, we need to understand the final state is 2A. The initial state is now 2B plus C. Therefore, the enthalpy of reaction is 2 times the enthalpy of A minus the enthalpy of the initial state. Now it's 2B plus C. Therefore, we can simply compare this expression and the previous expression and see the sign changes. Therefore, the result is simply negative 600 kilojoule per mole. I'll let you work on one practice problem. Let's calculate the enthalpy changes of two reactions. One is this. You start from 1B and 1/2 of C, and then you get A. Hint, this chemical reaction is exactly the same as this one, except that the direction is changed. And then, after you get this value, I want you to compute the enthalpy change of this reaction. Hint, this reaction is simply 4 times this one.